Okay, so let's give a thanks to Samay.
Yeah, thank you so much.
Thank you. So we'll switch to the next presentation. Will be presented by Dr. Yoomi Park from Etri, South Korea. She's a member of the supercomputing research section at ETRI, Daejeon. She received her BS degree in computer science from Sukmyung Women's University in Seoul, South Korea in 1991, and MS and PhD degrees in computer engineering from Chungham National University, Daejeon, in 1997 and 2010, respectively. Her research interests include high-performance computing, distributed deep learning, and database. And Dr. Park and her colleagues have been coming here to the MUG for the last 3 years. Okay, so let's give a big welcome to Dr. Park. Yeah.
Hello. Yeah. Okay. Yeah. Thank you, Professor Panda. Hello, everyone. My name is Yoomi Park. I'm working for ETRI. ETRI stands for Electronic and Telecommunications Research Institute. It is one of government research institutions in Korea. Now I am here today to introduce the SPRIM-K project to those who are to know it and to provide an update for those who are familiar with this project already. And SPRIM-K is the also name of the system it delivers. Here's an outline of my talk. First, I will introduce the background of this project. I will present an overview of this project. And then I will discuss the design and implementation efforts in more details. And finally conclude my talk by sharing what we have learned from this project and proposing our future directions. First, let me explain the background of this project. As you know, a supercomputer is the ultimate implementation of high-performance computing technology. So in this talk, I will use the terms HPC, research, and supercomputer interchangeably. Based on 2019 survey in Korea, Korea has supercomputing capabilities was significantly lower than that of other leading countries in both the number of systems and total computational power. While the HPC resources were limited, but demand from science and industry kept growing. Inevitably, many Korean institutions have been purchasing global supercomputers from the global vendors made in US and China. This table shows that there are supercomputers in top 500. There are many supercomputers made in US or China. At this point, we have to recognize that supercomputers are critical national asset. That any supply chain disruption could pose technological and national security risks. Therefore, Korean government has been striving to secure core technologies of supercomputer on its own. It has already established a second National Supercomputer Development Master Plan, along with an execution strategy consisting of 3 key pillars, like HPC application and can I move this? Yeah, okay. Application and infrastructure and system technologies. One of the most important components of this strategy was an accelerator technologies, which eventually has led to planning and launch of the SPRIM-K project. Building on this background, SPRIM-K aimed to develop our prototype of HPC system based on our own HPC accelerator, system software, and customized compute node for this accelerator. For clarity, I will refer to this accelerator as AB21. A project began in 2020 and continued until this September. To successfully carry out this project, we tried to bring together the country's capabilities. As you can see the slide, this project was carried out through Grand National Consortium involving 2 government research organizations, which is ATRI and KISTI, and 8 academic institutions and 2 domain industrial partners. The deliverables of this project are the result of close collaboration among these organizations. But however, I will not go into the details of the individual contribution into this talk. At the beginning of this project, we established the following R&D strategies. First, as you know, the most important thing is hardware and software co-design approaches for developing HPC Accelerator AB21. I will explain more details in the following slides. The second, we aimed to optimize data movement between host CPUs and AB21 chips by utilizing a shared virtual memory system. And third, we pursued full system integration by providing comprehensive systematic verification environments that includes software simulator, FPGA-based emulator, and silicon virtual prototyping. Fourth, we set up ways to carefully manage the risks and issues because it was very important because many different organizations were involved in this project. And fifth, to tackle the memory wall issues, we conducted a preliminary research on expanding memory capacity within a single node. Yeah, now I'm going to more detail. From now on, let me explain our HPC Accelerator AB21. This slide shows high-level architecture and implementation of AB21. The chip was in the left-hand side. The chip was built on ARM coherent mesh network integrated dual ARM cores, parallel processing units, and high-performance external interfaces, including DDR5 and PCIe Gen 5. Among them, the parallel processing unit is a core component of AB21 be responsible to execute parallel computation of AB21. I will go into more details in the next slide about it. And right side, you can see the actual image of die and package of chip. It was fabricated using TSMC 12 nanometer process node in the second quarter of last year. Its theoretical performance, peak performance is 8 teraflops for double precision floating point operation and 32 teraflops for single precision floating point operation. It contains 1.4 billion gates and approximately 4,900 boards for packaging. Now, this diagram shows the hierarchical architecture of the parallel processing unit in AB21 is the most important core component of AB21. The parallel processing unit is composed of 8 GEMIS clusters. Each GEMIS clusters is composed of 8 GEMIS and along with the clock, reset, power gating, and memory management unit. You can see a blinking component. And each GEMIS made up of 4 JAG-M and block of local memory instruction. Instruction. And each JAG-M is composed of JAG units and a single, JAG unit and a GEM units. A JAG unit is designed for processing open cell kernel based on RISC-V64G and custom instruction set, which is implemented to efficiently manage to gem unit. A gem unit is actually performs matrix parallel computation, which contains 16 operators, each of which can perform up to 2 double precision operations or 8 single precision operations simultaneously. Yeah, this shows a conceptual comparison among AB21 and the commercial GPUs and NPUs. NVIDIA GPUs support a broad range of numeric formats such as FP, double precision, single precision, and half precision floating point, and integer 8, B-flat 8, making it suitable for general purpose computing. While AB21 is specifically designed for high precision computing, so it's focused on the supporting double precision and single precision floating point operations. Making it ideal for fundamental scientific research and engineering simulation workload. In contrast, NPUs are specialized for AI inference and typically support lower precision data formats like FP16 or FP8 or integer 8, which is widely used in AI inference tasks. Compared to NPUs, AB21 is specifically designed for high performance computing, so scientific computing, not AI inferences. So making it fundamentally different from typical NPUs. And the table below shows compares AB21 with commercial GPUs, especially compared to NVIDIA V100, which used the same semiconductor process node, TSMC 12 nanometers. AB21 delivers about 14% better performance in terms of R-peak performance. Now I'm going to explain the software stacks for AB21. The most fundamental software component is a device driver, which manages AB21's behavior, including parallel task scheduling, task execution, memory access, and communication between host and AB21s. And AB21 adopts OpenCL programming model, which is one of the heterogeneous parallel programming models. So to support this model, the backend compiler and runtime system have been developed by enabling OpenCL kernel to execute on the AB21. And the backend compiler and runtime systems were extended based on LLVM Clang and Hoku respectively. We also customized the BLAS library for AB21, which support level 1, 2, and 3s. On top of this, the higher level libraries, MPP2 and HPL-like applications can run on the system. Before the chip was manufactured, we have developed and verified the chip design and software stacks step by step through several stages. Starting with the software emulator, we tested the software stacks on using emulator, FPGA-based test board, and finally, compute node equipped with actual chips. Next, let me introduce the compute node. We call it the silver node. The silver node is specifically designed to support the dual AB21 chips as an accelerator device. The silver node consists of 2 separate boards. One is a host board with commodity ARM CPU. We use the Ampere computing CPU, and the other is an accelerator board equipped with 2 AB21 chips. The 2 separate board design was adapted to shorten the project timeline through the parallel manufacturing and testing, and to simplify the system verification by enabling independent verification of each board prior to system integration. We are currently bringing up the accelerator board with AB21 chips, which is connected to host board through PCI interfaces, and testing software stacks for AB21. We are currently conducting various performance tests on AB21. This figure shown here represent the result of BLAS libraries, focusing on core operation like double precision matrix multiplication and double precision matrix vector multiplication. Those operations represent the majority of computation in both AI and science domains. And we continue to perform the test to gather more data and evaluate key metrics such as throughput, scaling efficiency, and power consumption. Here's what the system will look like at the end of the project. And left-hand side, you can see a logical view of a single rack scale HPC cluster consisting of 8 server node is a compute node, 2 management node, 1 storage node, all interconnected with InfiniBand and Ethernet. And right side, you can see a physical system of actual cluster. It includes partial two-phase liquid cooling system, which was also developed as part of this project. Last June, we showcased the selected component of full cluster configuration at International Supercomputing Conference 25, held in Hamburg, Germany. And our booth received a lot of interest and many questions from visitors. We actually have received questions like what is the purpose of this chip? Which process node was used? How is it different from NVIDIA GPUs? And is it commercial product? Yeah, I think you might be wondering the same thing. So I would say it's not a product version, it's just a prototype, but we actually have been co-developing it with one of Korea's family's company. Its name is Supergate. They has received full transfer of our all related technologies from us. So I think as far as I know, they plan to commercialize it in the future. Yeah, so what is the main takeaway from this project? I'd like to explain our Korea's HPC sovereignty has changed before and after the project. Actually, this diagram is hardware and software component of Nurion system. Nurion is Korea's 5th supercomputer, national supercomputer. And it also shows the which component were developed domestically and which component were sourced from abroad. You can see a Korean flag and USA flag or European flags. In Nurion system, only memory and management software were developed in Korea. After our project, the blue boxes and connecting line in this diagram highlights that the component that we developed through this project. Our HPC Accelerator AB21 and device driver, its runtime and compiler and BLAS libraries, and customized computing node for it. The second achievement from this project is the network we have built with global partners. As shown this slide, we have a formal and informal partnership with global leading partners. in Fabrica, semi-dynamics, ARM, and peer computing. In particular, our collaboration with Dr. Panda's research team has led to excellent outcome for the project derived from this project. So I'd like to say we are deeply grateful for their joint efforts. I'd like to share some thoughts on how AB21 could be utilized in the future. Since AB21 supports BLAS library level 1, 2, and 3 operations, it can accelerate a wide range of HPC applications that rely on BLAS libraries. Based on the outcomes, we foresee 3 potential application areas. The first, the fundamental scientific applications, which typically rely on high precision floating point operations, can benefit from AB21 by leveraging BLAS routines. And second, the AI training workload, which often use the single precision floating point operations, can be accelerated using AB21. And third, the scientific application integrated with AI can effectively utilize AB21 in both domains. In particular, AB21 becomes more effective when the application frequently invokes GEM or GEMB operation. This last one is finally, let me conclude my talk. What we've learned is so clear by taking a new path that no one in Korea had taken before, and walking it together. So we've proven that such achievements are possible by ourselves in Korea. Here's what I'd like to propose for the next step. We have already taken the first stride to HPC sovereignty in Korea. So this effort lays the groundwork for building our own national HPC ecosystem. From here, we should expand our vision beyond the HPC into AI and other future critical domains. And achieving this will not be easy alone, which is why close collaboration with global leading partners will be so essential for us. And finally, ultimately, we must keep going forward step by step, guided by Korea's national HPC roadmap. Yeah, that's all. Thank you so much.
Any quick questions? Yes, Sanjay, please use the microphone.
Thank you for nice presentation, Dr. Park. I think it's very impressive to see national level HPC STEM progress. My question is it seems like it's more focusing on the software than last year. It's keep evolving to software level. Do you have any plan to test the MPI like EMA pitch